Hi, I'm presenting deep learning project to you, which is pneumothorax classification based on ResNet 18. My name is Yang, and we also got Wang and Shangke in this group. In this presentation, we are working through the introduction and the objective of the project, the structure and visualization of the data, the model architecture, and the results it produced, and most importantly, the conclusion of the project. First of all, I want to talk a little bit about the pneumothorax and its diagnosis. So pneumothorax is a collapsed lung, which is a severe physiological condition. As we can see in the figure, the patient's left lung got compressed and its periphery is filled with air, which is really putting the patient's life on risks. One way to diagnose pneumothorax is by doing chest X-ray, but that method is also facing some challenges. As we can see in this figure, the patient's right lung got pneumothorax, but we can hardly tell the difference without any education in radiology. But even for people who got radiology education, the diagnosis is heavily dependent on their subjective evaluation of radiologists. So we want to build a new method to mitigate such conditions, and that brings to our objective.
As we can see from the previous introduction, our project is to develop a pneumothorax classification model from chest X-ray images to facilitate diagnosis.
For the data we're using, we are following 80, 15, and 5 splitting rules. We are dividing 5,855 JPEG images into 80% training images, 15% test images, and 5% validation images. And since we want to enhance our image analysis, so we also did data augmentation.
So for loss function of our model, we use focal loss, and the focal loss function can help to mitigate the impact of class imbalance by giving more weight to hard examples and less weight to easy examples. This is achieved by introducing a hyperparameter called gamma, which controls the degree of downweighting of easy examples. And the focal loss function is defined as a subclass of NN dot cross entropy loss in our code. For batch size, we use 32, and we set the 10 to the degree of -3 as learning rate, and we train our model for 50 epochs, and the most importantly, we use ResNet 18 as our model architecture. So ResNet 18 is a deep convolutional neural network architecture that has shown great success in various CV tasks, including object detection and image classification. In the context of this classification task, ResNet 18 has been used as the backbone of deep learning model to detect and segment the chest X-ray images. And ResNet 18 has the ability to learn complex patterns and features from images, making it a powerful tool for medical image analysis. Its architecture includes residual blocks that allow for the efficient training of deep neural networks, making it an ideal choice for this task. So during the model training process, we firstly train a model by passing the training dataset first, and we calculate the loss for that epoch, and we perform backpropagation through the whole CNN model and the computed accuracy and loss on training dataset. After that, we run validation and calculate the AUC for our validation dataset.
So after running 50 epochs, we can see the results here. From the loss curve on the left, we can see that the loss during training process was fluctuating but with a descending trend, and hits below 0.1 after a couple epochs, which shows a good performance on the training sets. For the test sets, the loss is also fluctuating but descending with a conversion value around 0, which also indicates a good performance. And the accuracy curve is on the right. Both the training and testing accuracy oscillated but finally hits around 96% and 99% accuracy respectively, which exhibits remarkable classification performance.
Finally, let's make a conclusion that based on the experiments that we did in this project, our model is very effective in learning the features of the dataset, and our algorithm is making accurate predictions based on the dataset, X-ray dataset.
So here's all the content we want to present. Thank you for your watching.